Many times a week, I receive a question from our friends, followers, or even from our corporate customers. Should we use Docker or should we use Kubernetes? They believe Docker and Kubernetes are two alternative technologies and they have an option to select either or. If you also have the same confusion or if you want to learn Kubernetes, then you are at the right place. Hello, fellow tech enthusiasts, friends, and families. Welcome to our new course. Kubernetes is always a difficult subject to tackle, especially if you are beginner to this domain. Then it can seem like a mythical creature. If you follow today's session without skipping any content, you will have a complete understanding on the basic concepts of Kubernetes. Let's find the answer for all the questions you may have. Before we begin, if you are new to our channel or haven't subscribed yet, please subscribe to our channel and please click on the bell icon to get notification for any new topics. We regularly upload videos on different cloud offerings, microservices, DevOps, and many other topics. We'll start with today's course outline. We'll begin with introduction to containers, followed by what are the challenges we observe in containerized platform, how to overcome those challenges. Then we'll talk about what is Kubernetes. We will review Kubernetes architecture, followed by different Kubernetes components. Then we'll review how Kubernetes work, followed by we will discuss different Kubernetes objects like pods, services, deployments, replica sets, and others. Then we'll review Kubernetes manifest files, and at the end, we'll review how to manage Kubernetes clusters. Throughout the course, we have used real-life examples and animations to make the session effective, interactive, and easy to understand. If you encounter any challenges or have trouble understanding a concept, please note down the timestamp and leave a comment. I will do my best to clarify you. We have a lot to cover, so let's jump right into it. We'll start with monolithic application. Let's understand what is monolithic application. In monolithic applications, all the modules, all the code are jumbled together in a big jumbo application where you have overlapping domains, overlapping codes, everything you are running in one application or one code base. Now, with the rise of microservices, we are trying to break those components or the business components into separate services such that services can run independently, services can scale independently, services can be deployed or run as Docker containers. These containers can run in physical machines, virtual machines, or cloud VMs, or even inside a cloud managed environment like Google Cloud Run or AWS Fargate. For today's demo, let's assume we have a web application. Our front end is in Node.js, database is PostgreSQL, and we have a caching layer which is made out of Redis. We are running our application in a virtual machine. We have one load balancer, which is balancing the load between the containers, and that load balancer is exposing the application into external world. Now, since we have set up container auto scaling, if our front-end part or the Node.js container is getting more and more load, it will automatically launch a new container. Even more load, it will again launch another one front-end container or Node.js container. Now, if our database is getting more and more read request, you can see we do not have space in this virtual machine, or we do not have CPU or RAM available in this machine to accommodate another one container. Although we have configured container autoscaling, one point we have to remember, container autoscaling is not equivalent to node autoscaling. We have to separately configure autoscaling for the nodes where we are running those containers. Once a new node is available or launched, then we can run that new container on this new node. Now, it's not only the configuration, these are all manual tasks, or manually we have to perform provisioning, resource allocation, availability, load balancing, scaling, health monitoring, and security. All these tasks we have to perform or manage manually. Now consider a use case or an enterprise application where we are running thousands of containers. How tedious that task could be. You can pause the video and think, what is the alternative to manage all these tasks automatically? To automate this task, if you are thinking a container orchestration platform, you are in the right track. Yes, we need Kubernetes or container orchestration platform that can help us to automate all those manual tasks, and we can effectively run hundreds or even thousands of containers. Now, I believe you got the answer for the first question, either Docker or Kubernetes. The answer is Docker and Kubernetes are not either or selection. Docker is used to run containerized applications or containers, whereas Kubernetes is used to orchestrate those containers. Let's review what is Kubernetes. Kubernetes is open source container orchestration platform developed by Google. Kubernetes automates the deployment, scaling, and management of containerized applications. If you have hundreds or even thousands of containers, Kubernetes can help you to manage those containers and run in a physical server, in a virtual machine, or even in cloud virtual machines. Kubernetes is a declarative configuration file to define the desired state. Now you must be thinking, what is declarative configuration? Let's understand the concept using an example. First, let's understand what is imperative way. Let's assume that I have point A and I want to go to point B. The first option is I can drive. If I am driving, I have to monitor first. I have to go right, left, right, left. I have to keep track of the entire route from point A to point B. Now, in a declarative way, the option would be I will hire an Uber or a Lyft from point A. I will specify I want to go to point B. Now, the Uber driver will take me from point A to point B. I really do not have to care what is the speed limit, what is the route, is there any stop sign. I don't have to manage and monitor all those aspects. Using this concept, Kubernetes can help us to manage our platform. That means we will specify our desired state. When users describe how they want their application to be configured, and we can use a YAML or JSON file, Kubernetes will ensure that the actual state of the application matches the desired state that we are specifying in the configuration file. We call it as Kubernetes Manifest file. If you see this Kubernetes file, we are specifying the replicas, that means number of Kubernetes containers we want to run in our application and what type of container. If you haven't seen a Kubernetes manifest file, don't worry. We will review those different components in a later slide. But let's assume that we have this Kubernetes manifest file. We are specifying what type of container, that is Nginx, where the image is latest, and how many replicas I want to run. When I will execute this Kubernetes manifest file, it will create those containers with 5 replicas or 5 instances. At any point of time, if one of the pod dies or if it crashes due to different reason, maybe the container inside that pod crashed, it does not have the resources to run that container, then Kubernetes will launch a replacement pod on top of that. Kubernetes also provides out-of-the-box features like deployment automation, scaling, high availability, disaster recovery, and container management activities like load balancing, service discovery, and also self-healing capabilities. Now let's review Kubernetes architecture. A Kubernetes cluster consists of set of worker machines called nodes that run containerized application. Every cluster has at least one worker node. Then there is a control plane that manages the worker nodes and the pods in the cluster. In production environment, the control plane usually runs across multiple computers, and the cluster usually runs multiple worker nodes because we need to think about fault tolerance and high availability. Let's say if one worker node dies or crashes, then my cluster should not crash or my cluster should not stop working. I should have enough resources to run those containers. In these worker nodes, we run different containers. To manage these Kubernetes containers, there are different components. To start with, kubelet. Kubelet is an agent that runs on each worker node in that container, and it will run all those daemons and the necessary processes to run those Kubernetes pods. Then there is a second component that running in the worker node. It's called kubeproxy. And kubeproxy is a network proxy that runs on each worker node in the Kubernetes cluster, and it is responsible for networking. Then moving to the control plane, there a component called API server. API server, this is the gateway or the front end of the Kubernetes control plane, and it exposes the Kubernetes API either to a web UI or Kubernetes UI, or could be the CLI, or you can access the Kubernetes control plane using APIs. Next, there is another one process running called Kubernetes scheduler. Kubernetes scheduler manages the placement of new containers inside the pod based on the hardware, software, policy constraint, affinity group, anti-affinity specification, data locality. It manages everything, and based on all those parameters and constraints, Kubernetes scheduler places those containers inside worker nodes. The next component is Kube Controller Manager. Kubernetes Controller Manager keeps track of the cluster. There are many different types of controller. It could be node controller, job controller, endpoint slice controller, or even service account controller. Then the next component is etcd. Etcd is a highly available key value store used by Kubernetes to back all the cluster data. If your Kubernetes cluster is using etcd, then you have to make sure you have a backup plan for the data. If you want to take backup of your Kubernetes cluster, you can use etcd and take the backup from there. There is one more component, it's called Cloud Controller Manager. This component is responsible for cloud specific controller logic. The Cloud Controller Manager lets you link your cluster into cloud providers API. If you are running your container in on-premise systems, maybe physical machines or virtual machines, then this Cloud Controller Manager will not be applicable. It is only applicable for your Kubernetes clusters running inside cloud. Now let's review different Kubernetes components. To start with, pods. Pods are smallest deployable units inside Kubernetes cluster. Now, if you have a container application, it could be a Docker container. Kubernetes adds an abstraction layer, and you don't interact with the Docker or other container technologies. We just interact with the Kubernetes control plane to manage our containers. And this Kubernetes pod create running environment or layer over the container. As I mentioned, it is an abstraction layer that abstract the implementation of the container, and you can run those pods in a Kubernetes worker node. When your application is receiving more and more traffic, it will scale out, or that means it will replicate number of pods. Once your application load will go away, it will scale in and it will remove the other containers or the additional containers. Normally, a Kubernetes pod will have a single application container. It could be a database container, it could be application container. Normally, as I mentioned, every pod will have a single container. But there are instances when you must run multiple containers inside one pod. Let's see one such example. Let's say you have your primary application or the Docker container is running. On top of that, you want a helper container which will extract all the application logs and put those logs into a S3 bucket. If you have some setup, then it is called sidecar container. In sidecar containers, we have multiple containers running inside one pod. But as I mentioned, majority of the time you should have one application running inside one container. Now let's understand a simple Kubernetes manifest file and let's see how pod works or how the pod lifecycle works. To start with, you should have a version. Then, what is the kind? It is more important. If you are creating a pod, the kind will be pod. If you are creating service, the kind will be service. Kind will define what Kubernetes component you are trying to define here. Then the metadata, inside metadata will provide the name, what is the name of the container, followed by the specifications where we are providing specification for the container, what is the name or what software I am running, what is the image, and you can see that this is the Docker image we are running, what is the port, that is the container port is 80 for us. This is a simple Kubernetes manifest file. As I mentioned, this is a declarative language where we are specifying what is the container application that I want to run inside the pod, what is the name of the pod. Now, once I will execute this Kubernetes manifest file, it will create the pod, and let's understand the pod lifecycle. The first stage in the lifecycle is pending. In the pending stage, the pod has been accepted by Kubernetes cluster, but no containers are running. The next stage is running. In this stage, the pod has been bound to a node and all the containers have been created, or at least one container is still running. The next state is succeed. Succeed state means all containers in the pod have terminated successfully and it will not be restarted. There could be another one state that one or more container termination failed. That means it's not terminated successfully. That could be a failed state. There is one more state is possible and we call as a unknown state. For some reason, the state of the pod could not be obtained. So these are all different state that defines the pod lifecycle. Let's review Kubernetes services. Let's understand how the pods inside a worker node communicates with each other. Let's assume we have a LAMP stack application and we are running our pods inside a virtual machine. We have our front-end pod, which is Apache. We also reviewed the Kubernetes manifest file to maintain or create those pods. When we will execute that manifest file, it will create or launch the pod. Kubernetes will assign a private IP to each pod at the time of creation. Naturally, my pod will get a private IP. Let's assume the IP is 10.10.100.150. My application will have a database pod, that is the MySQL database pod. The database pod will also get a private IP from Kubernetes, which is 10.20.100.120. Using this private IP, now front-end pod or the Apache pod will be able to establish communication to the database pod. While the application is working, let's assume my front-end pod crashed because maybe the container inside the pod destroyed or damaged or it does not have proper resources. As soon as the pod will be crashed, Kubernetes will launch another one replacement pod on top of that, and it will assign a new private IP to that. Now, since I got a new private IP, this communication can be disrupted. That is why we need a static or permanent IP address with this pod. Kubernetes provides this with the concept of services. Services is a Kubernetes component that will assign static or permanent IP addresses to each of my pod. As I mentioned, containers are ephemeral. If you are connecting using IP addresses, then it's difficult to manage the dynamic IPs and you need to modify your existing application as soon as the pod will die. Services will help us to communicate using that permanent IP. And now the pod lifecycle is not directly tagged with the service lifecycle. If my database pod will die or a new replacement database pod will come, still the same IP address or the private IP address will be maintained and my application will not be disrupted. With the concept of service, I'll be able to still establish communication from my front-end pod to my database pod, and I do not need to change any configuration to run my application. Now you must be thinking how to expose these services externally, since this is all private IP addresses. How can I access my containers from internet? To communicate with internet traffic, I'll use something like that, http:// then the IP address and the pod port. Now, if I want to establish communication with my front-end pod or the Apache pod, my front-end pod URL should look like 10.10.100.140, that is the IP address, and 8080 is the port for Apache. Using this URL, I'll be able to establish communication from internet to my front-end pod. But my database pod, it should not be directly exposed to internet, because database should be accessed only from my web application. It should not be exposed directly to internet. That means if I have that URL or if I have created the URL with the IP address and the port 3306, which is the port for MySQL, this should not allow me to expose my database. Even if I'll hit this URL, the traffic should not come or reach to my application. That is why we have the concept of external services and internal service. If I'll define that service as external service, I'll be able to expose the traffic to internet. If I'll create an internal service, then my application will not be accessible by default from internet. I must specify the service type at the time of creation. By default, the service type will be internal services. Now, if you observe this URL, this is not the regular URL. Normally, we try to access some URL like HTTPS. There should not be exposed with HTTP. There should be some SSL or TLS certificate or the secured. And then there should be a domain name instead of this IP address and the port. But services does not give that capability to expose your pod or application using that domain name. Then what is the answer? How can you do that? The answer is Kubernetes Ingress. Ingress manages external access to all these services. Let's assume that we have our previous example where we have one Apache pod and a MySQL pod with those services. These services is attached to this pod with a static or permanent IP address. Now I'll define ingress at the container level. When the external traffic will come from internet to that ingress, ingress will have routing rules that will route the traffic to all my pods. Now in production, you might have more than one nodes because of high availability. You are not going to work with one node. In that case, if you have more than one node, routing will be able to route traffic between different nodes in your application. So routing is not on a node level, it is on a cluster level. Ingress has the capability for traffic load balancing, SSL or TLS termination. As we see, we can expose the URL using HTTPS, and it can work as a name-based virtual hosting for you. Now let's understand a different scenario here. In our previous example, we have the Apache pod and the MySQL pod. And let's assume that MySQL pod has crashed. Then the container state will not be saved because my containers are ephemeral containers. On-disk files in a container, as these are ephemeral, the problem will occur when a container crashes or stopped. The container state will not be saved. All the data that was created during the lifetime of the container will be lost. During a crash, Kubernetes will restart the container with a clean state. And that is a problem, right? I have all my databases or all my data, whatever the transactional data I have written inside the database, it will wiped out. How my application will work? Let's consider another one scenario. Let's assume we have multiple nodes and these containers is doing some local processing or doing some local file processing. If I want to share files between these pods, in my current setup, I won't be able to do because these pods will work in isolations. These are ephemeral. If any pod will die, then that particular file content will be lost. So for file sharing, we need a network storage where we can process those files, put those files, and get access to all those files. And this leads to a requirement that my storage should not depend on the pod lifecycle. My storage unit must be available to all worker nodes. And the answer is Kubernetes Volume. This volume could be the physical storage inside the node or the node's local storage, or it could be a remote network storage for that volume, or it could be associated with a remote or network storage. Here is a sample Kubernetes Manifest file that can help us to create a persistent volume. Now, if you'll pay attention here, for this case, the kind is persistent volume. Now, in the metadata, first we have a name that we have to specify. Then the specification, I have capacity, that is what is the storage amount. This will give me 5 GB of storage, and this volume mode, this is the file system. We'll discuss the access mode, how I want to access my disk, and all other attributes this will have. So this is a simple Kubernetes manifest file which will create a persistent volume for me. Kubernetes offer 3 components to persist the data inside Kubernetes. One is persistent volume, second Kubernetes volume claim, and third Kubernetes storage class. Let's understand all those concepts one by one. We'll start with persistent volume. Kubernetes definition of persistent volume tells it is a piece of storage in the cluster that has been provisioned by an administrator or dynamically provisioned using storage class. And in this video, we'll see both the examples that how an administrator can provision or how we can provision dynamically. We already reviewed this manifest file and we have seen that what is the kind? The kind is persistent volume. And here I have 5 GB storage, file system, and read write once is the access mode. We can create the persistent volume using this manifest file. And this persistent volume, it's an abstract storage component and it can be associated with a physical storage. It could be associated with network storage or the cloud storage like EBS, blob, or even a physical storage like NFS files here. And it can work as a cluster of volumes. We can have multiple volumes of different sizes and different access mode. It can work as a cluster. Now let's understand the access mode. The first one is read write once. Read write once means volume can be mounted as read write to a single node only. As the name suggests, read write once. That means it will allow both read and write operation to only one node. Read write many, as the name suggests, the volume can be mounted as read write by multiple nodes. It will provide both read and write capacity parallelly to multiple nodes. And the third is read only many. That means the volume can be mounted as read only. It will not support any write operation and it can be mounted to many nodes. The next question is how to attach this persistent volume with a Kubernetes pod. And the answer is we can't directly use persistent volume in the pod. To attach this or to attach this volume with pod, we need persistent volume claim. Persistent volume claim is another one Kubernetes resource where we configured how much storage our pod needs. Again, this is a Kubernetes manifest file to create persistent volume claim. That is why you can see the kind is persistent volume claim. The access mode is read write once and the storage amount is 8 GB. When we create this persistent volume claim, with the storage and the access mode we have specified, persistent volume claim will find out the appropriate volume available in the cluster and binds with it. Now, once we'll create that pod and once we'll specify this persistent volume in the pod manifest file, the kind is pod and the volume type is the persistent volume claim. The pod will locate the persistent volume claim and it will attach the pod with the persistent volume. This is the way we can create persistent volume and we can attach the persistent volume with our pod. But if you observe, this leads to a different issue. Now, because of the persistent volume claim, the pod creation now got a new dependency, and the persistent volume must be available or created beforehand. The question would be, how can we dynamically create the persistent volume and attach that with pods? The answer is storage class. Storage class provides a way for administrator to describe the class of storage that they want to attach. This is a sample storage class manifest file where we have the kind as storage class and we are provisioning an EBS volume here. We are associating an EBS volume for the storage class. The type is IO1 and the IOPS per GB is 50 and we are encrypting that file or the volume and the volume will be in USTist 2C. This is a sample Kubernetes manifest file to create the storage class. When we'll execute this Kubernetes manifest file, it will create a storage class. Now, when I'll create the persistent volume claim, I'll specify the access mode and then I'll specify the storage volume, how much volume I need, and then the storage class name instead of specifying the persistent volume name. Now, the persistent volume claim, it will associate with the storage class and the storage class will create the persistent volume for me dynamically using an EBS volume. And that is how you will be able to manage the dynamic creation of your persistent volume at the time of pod creation. In our previous examples, we saw that we want to connect my pod or the front-end pod with the database pod, MySQL pod. This is a simple Kubernetes manifest file to create this pod. In this example, I have all those database attributes that I have coded in my pod manifest file in terms of the name of the MySQL host, the user, password, the database name, everything. And these are the values that I have hard coded in my manifest file. Now let's assume I have to parallelly run a non-production environment. Do I need to maintain two different manifest files for that? And even if I change a small thing in that manifest file or any value in that manifest file, I have to first update. Then I have to rebuild that one. I have to create that image, push that image container image to that repo. Then I have to again deploy, which is not portable. I have to manage and maintain environment-wise Kubernetes manifest file. Then what is the solution? How can I externalize these configurations? The answer is Kubernetes config map. Kubernetes config map will allow you to decouple environment specific configuration from your container images so that your application are easily portable, and config map stores all those non-confidential data in a key value pair. From your pod, you can consume this config map as environment variable or a command line argument or as configuration file in a volume. Config map you can mount as a data volumes inside your pod. Once you have the pod and let's say we have our configurations in a config map, before connecting the database, my front-end pod will get the configuration, that means all the database attributes, and then it will establish the communication. This is an example manifest file. This is the Kubernetes manifest file to create my config map. If you remember the previous example, all the database attributes was available as part of my pod manifest file. Here I have externalized the configuration. That is why my kind is config map here. The name is MySQL config, and here I have all those parameters mapping. It's a key value pair. The key is MySQL host, where I will have the host name, then the user and the database type. With this, I'll be able to modify my pod configuration. Here, the kind is pod, and if you see that my config map reference, here I am specifying the config map name. This is the config map name. I am specifying instead of directly coupling them or hard coding them inside my pod manifest file. But one point we have to remember here, config map does not provide secrecy or encryption. Then you must be asking that is config map applicable to store my passwords or user IDs? The answer is no. Kubernetes provides another one component called secret. A secret is a Kubernetes object that contains a small amount of sensitive data, such as password, token, or an API key. Secrets are very much similar to config map, but these are specifically made to hold confidential data. But one point you should remember, while configuring the Kubernetes secret, you should take care of this, and this is very important. Kubernetes secrets are by default stored unencrypted, and it's stored in a control plane, that is the etcd of the application server. That means Kubernetes secrets by default stored unencrypted in the API server's underlying data store, or the etcd. Anyone with API access or with access to etcd can retrieve or modify a secret. Additionally, anyone who is authorized to create a pod in a namespace can use that access to read any secret in the namespace. Then the question is, how to protect these secrets? You must take these measures if you want to protect all those secrets. You should enable encryption at rest, and you should configure resource-based access policy, or RBAC, with least privilege access control. You should restrict secret access to specific containers. You should not keep it wide open. Or you can use external or cloud native secret stores like AWS Secrets Manager or HashiCorp Vault for this purpose. So instead of using the secrets, you can store the secrets in AWS Secrets Manager, HashiCorp Vault, or any other cloud native secret store, and maintain your external configurations, which is not secret, like the database name and all, in a config map. So far, we have discussed and we have reviewed that we are running our application in one node, where we have one front-end pod and we have our database pod. But we have to maintain the high availability of our application. That is why we must use multiple nodes. And we have reviewed that we have services with that pod, which is not associated with the pod's lifecycle, and services will provide a persistent static IP or permanent IP address with DNS name. And we also have Ingress. Ingress will provide traffic load balancing. That will help me to distribute the incoming load between my different pods. When my application will receive more and more traffic, it will launch new pods. And once the traffic will go away or the load will go away, it will automatically remove the pods. Now the question is, how can we manage or maintain, or how many pods your application should have? Or how can we maintain the minimum number of pods? To do this, we have to create pod replication, and to replicate those pods, we must create a blueprint. And then using that blueprint, we can scale out or scale in the number of pods based on the application load. So once my application will receive more and more load, it will scale out. Once the load will go away, it will automatically scale in. To do that, we can configure the following manifest file in Kubernetes. And if you say here, my kind is deployment, and this process is called Kubernetes deployment. Kubernetes deployment can create an abstraction layer on top of that pod, and it will help us to manage and maintain my pod, or auto scaling my pods. It will help me to maintain minimum number of pods. Let's review this Kubernetes manifest file for deployment. Here the kind is deployment. Here I have the template where the application is Apache, and my container type, this is Apache container. Container image is HTTPD 2.4 and the container port is 80. Now, if you pay attention here in the specification of my deployment, I have replicas as 4. That means I should have 4 pods that is running. Once the application will receive more and more traffic, I can scale out or max search to 6. It can go down if the loads are not there to minimum of 2, not less than 2. And with the help of this Kubernetes manifest file for the deployment, I will be able to manage deployment of the pod. And as I mentioned, deployment creates an abstraction layer on top of the pod and maintains the number of running instances in a Kubernetes cluster. For our real-life enterprise use cases, we will mostly work with the deployments and not directly with that pods. If any pod will crash, user request will be processed by other available pods, and this will provide us a high available application, and our application will be able to serve traffic even if one pod is die or one pod has crashed. Now you must be thinking, wait a minute, I have only replicated my application pods. How about my database pods? What will happen if my database pod will go away or if my database pod will crash? What I'll do? Absolutely, you are correct. We must implement the replication for database pod will. But the database pod cannot be replicated using Kubernetes deployment. The reason is database is stateful, it's not stateless. That means every time when I'm writing the data inside my database, the changes in the data, it must be replicated across the node. And for that, I must use a permanent volume or external storage, and my database should communicate with that. And there, I should maintain or synchronize the read and write between these pods, such that if one pod is trying to access the data while other database pod is trying to write, it should not create any data consistency issue. I must avoid any data consistency problem. And to do that, we need to use StatefulSet. StatefulSet will help us to do the similar thing what I have done, the replication using a deployment for application pod or for stateless application. StatefulSet will help me to do that deployment or replication for my database. And please remember, the StatefulSet is applicable only for applications like databases where we have to maintain the state of the application. To summarize, deployment can be used for stateless application replication, whereas StatefulSet to be used for stateful app replications. So when we are talking about replication, we'll create a template. For stateless application, we'll use deployment. For stateful application, we'll use StatefulSet. Now with this, even if my entire node is not available, then also my application will be able to serve traffic, because my application, the database and the front end is replicated to another one node or maybe to another one region. With that, on my cluster is replicated across multiple nodes. Now I have created a true or highly available application architecture for my web application. In today's video, we have covered multiple Kubernetes components, and it is very easy to get confused with the purpose of each component, especially if you are just getting started or new to this world. Now let's summarize all the components that we have covered today and their purposes. We'll first start with Kubernetes cluster components that we have covered. To start with kubelet, we saw the kubelet is the node agent that is running on each worker node. just like the Docker daemon here. The next component we reviewed, Kubernetes proxy or kube proxy, and it handles the network communication inside the cluster between different nodes. Then we reviewed API server, and we saw API server that runs inside the Kubernetes control plane, which works as a gateway to access the Kubernetes cluster, the Kubernetes UI, the Kubernetes CLI, or even the APIs will be able to interact using this API server with the control plane. Then we have reviewed scheduler. Kubernetes scheduler schedules pods inside that nodes. We also talked about Kubernetes controller manager. Kubernetes controller manager runs controller process inside the clusters. We reviewed etcd. This is the highly available key value stores to store all cluster data. If you want to take backup of your Kubernetes cluster, you will take backup from etcd, and you should create the replication mechanism of your etcd. Next, we reviewed Cloud Controller Manager, and we saw that it is only applicable when you are running your Kubernetes cluster in cloud environment, and it interfaces with cloud providers like Azure, GCP, AWS. Then we'll move to Kubernetes other components. And to start with pods, we saw that this is the smallest deployable unit, and it is the abstraction layer on top of the Docker containers or any other containerization techniques. We reviewed services, that is the communication policy to access between the nodes, and services are not tagged to the pod lifecycle, and it will provide a static or primary IP addresses to each pod. We also reviewed Ingress. Ingress manages external access, and it provides traffic load balancing and route the traffic to the services inside a cluster. We also reviewed Volume. Volume provides persistent storage to all the containers. We also reviewed config map, which helps us to decouple configuration from container. We also reviewed secrets. Secrets store sensitive information, credential, API keys. Please remember, you should enable encryption at rest. You should create that access control or granular level of access control with least privilege. If you have any secrets, you should use cloud providers or external secrets like AWS Secrets Manager, HashiCorp Vault instead of using secrets. We also reviewed the deployment, and deployment is the blueprint to replicate any stateless application. Last but not least, we reviewed StatefulSet. StatefulSet is the blueprint to replicate stateful applications like databases. With these Kubernetes components, now you can create powerful Kubernetes clusters for your enterprise application. If you want us to create a dedicated video or a detailed video on Kubernetes with hands-on demo, please drop your request as comment to this video. Happy learning, and thank you for your time. Before we conclude today's video, I would like to request you, if you are new to our channel or haven't subscribed yet, please subscribe to our channel and please click on the bell icon to get notification for any new topics. We regularly upload videos on different cloud offerings like microservices, DevOps, and many other topics. This was all for today. Thank you. Happy learning, and we'll see you in our next topic soon.